Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to discuss dangling pointers. So in this lesson, we will first review what happens when we call delete. We will see that pointers continue to hold onto the addresses that are assigned to them. You can still access and manipulate this deallocated memory. This can lead to some very difficult to find bugs. The solution is straightforward, but it requires rigorous control on the value of local variables. Now, a pointer has a value. If the value is null pointer or the zero address, this is a known invalid address. If you ever try to dereference or access the memory at this location, you automatically have your program terminated. Now, if initialized or assigned to a value returned by new, the pointer then stores a valid address. However, once memory is deallocated, it's no longer valid. A dangling pointer is a pointer that stores an address that is no longer allocated. It is important to remember that all delete does is pass the value of the operand to the operating system to let it know that memory is no longer required. If we run this code, notice that both before and after the delete statement, the local variable p_value maintains the same address assigned to it, that same address that was returned by new. Because a dangling pointer still stores an address, it's similar to a wild pointer, only the behavior is much worse. A wild pointer is almost certainly invalid except under very peculiar circumstances. A dangling pointer, on the other hand, stores an address that has previously been allocated. Now, operating systems may flag deallocated memory as being available, but it may not waste the time to flag it as no longer being allocated to one specific program. This is actually quite reasonable. If a program has been asking for memory, it's likely it's going to continue asking for memory. So in that case, why not just continue to reuse the memory that was sent back when that same program asks for additional memory? Unfortunately, if another program asks for memory and no more memory elsewhere is available, it may then reclaim deallocated memory that was previously assigned to another program. Now, if you make two separate independent requests for memory, then you're going to get two different addresses. So here, both the pointer to value 1 and pointer to value 2 have different addresses, as we can see from the output. The problem is, if memory has been deallocated, the operating system is welcome to reuse that memory for future requests. So here, the memory for pointer value 1 is allocated, displayed, and then deleted. When memory is requested for pointer to value 2, you will notice that it happened, at least in this case, to get that same memory location. Now, one thing that's interesting is the same memory could now potentially be used for two completely different purposes. Here, for example, p-value 1 is storing a long. Now, I allocate memory for a long and then I immediately delete it. Next, I have p-value 2. It's a pointer to a double and I allocate memory for a double. Now, it happens that I got lucky and I was allocated the exact same memory. So I can now print out the value stored at p-value 2, and it is indeed, as we would expect, 91. However, notice that I did not set p-value 1 to null pointer. it still contains the same address that is now assigned to p-value 2. So now p-value 1 being assigned to that location the value 150 interprets those 8 bytes as a long. And so it places an integer there that satisfies such a description. So when we print out p-value, the value stored at the location p-value 1, it is interpreted as an integer, 150. However, if we now try to print what was there interpreted as a double, after all, that is what p-value 2 is pointing to, we get something very bizarre. We get 7.41098 times 10 to the negative 322. This is actually what happens if the bits that store 150 are interpreted as if they were a double precision floating point number. So if you accidentally reuse a local variable that has been deallocated, you may get very unlucky and you may now be using the same memory location for two completely different reasons. So a small thought experiment. Imagine what may happen if you're using two pointers, one dangling off of the other, both of them having the same address and both of them being used for similar purposes. So if you have that dangling pointer, you may be assigning to that same location with similar values. So if you're focused on the one that is not dangling, you're looking at that memory location and it's 5, and then all of a sudden it jumps to 7. But you have no clue why it's jumping to 7. Nowhere did you ever reassign what was at that address to 7. It was supposed to be 5. And then you're looking through your code, trying to figure out where you accidentally assigned that a value of 7. And of course you never will find it because it was the dangling pointer that was being assigned to 7. Now, fortunately, there are tools in the debugger to actually catch this. You can have the debugger stop whenever a particular memory location changes, but that's an advanced feature. Now, I've said before that there's always the possibility that between deleting a pointer and trying to assign to it, there's always the possibility the operating system may take that memory away from you. Just to show you how seldom it is, here I have an example. p_value is assigned the address of a dynamically allocated integer. I then immediately delete it. Now here we see that we have a for loop going from 0 up to 1 billion. The purpose of this is to give the operating system a few split seconds to possibly reclaim this deallocated memory. Having done so, I then try to assign to that memory location. Now, before this happened, I actually had to run it 57,368 times before one execution of this program failed. So it can be very rare indeed. Now, dangling pointers can always be solved by assigning deallocated pointers the value of null pointer. So as soon as you delete, assign that local variable the value null pointer. You should be assigning deallocated memory the value null pointer even if that function is exiting. Otherwise, a wild pointer may subsequently pick up that value. Now, things can become a little bit more difficult if multiple pointers are assigned the same address. So for example here, p-value 2 is simply being assigned the value of, or the address stored in p-value 1. The problem is, here I deallocate the memory at address p-value 1, and I judiciously set p-value 1 to null pointer. Unfortunately, I may have forgotten that p-value 2 also stores that same address. Now, in this small little toy example, of course it's obvious, but consider a much larger program. It may very well be likely that the same address may be spread throughout multiple locations. So here, we will notice that p-value 2 continues to store that same address, nothing has changed, but not only that, I can assign to that location and I can print what is at that what has been newly assigned. So if we execute this code, we notice that yes, p-value 1 and p-value 2 have the exact same address, and I was able to successfully assign to p-value 2 even though the memory associated with it has already been previously deallocated. The single greatest difficulty for students studying algorithms and data structures is the belief that delete does something magical. Important, the statement delete a pointer to some data does nothing more than send the address to the operating system to flag it as now being available. That's all that happens. It doesn't reassign or set to null point. It doesn't do anything else. It's just sending an address back and saying, oh, by the way, the memory you gave me that was located here is no longer needed. Thanks and so long, and thanks for all the fish. Okay, so following this lesson, you now understand that delete does not change the value of a pointer, nor does it do anything magical. It just sends an address to the operating system. You know that calling delete on a pointer allows the operating system to flag that memory as being available, and the operating system, however, may choose to leave that memory allocated to that executing program, usually. To avoid dangling pointers, it is important to assign to any local variable the value null pointer. Doing so prevents any other pointer, or even that pointer, from accidentally being reused at some point in the future, perhaps being still able to access that memory location. Otherwise, remember, delete does nothing to change the value stored in the pointer. Here's the references, the colophon, and a disclaimer. Cheers!